Hello guys, welcome once more to another video again in my YouTube channel. So in today's video, we will be looking at the Cameroon GCE A-Level Math June 2017, question 4 of paper 2. Okay, so as displayed to you on your screen, you can follow me on the YouTube platform via Mathematics Dreamland for Africa, or by simply just inputting this name here on the search bar, MDLFE. They will take you directly to my YouTube channel. Okay, all right, and you can equally reach me on WhatsApp via the telephone number displayed to you on your screen. So guys, today I appreciate everyone who is watching this video for today, and please I recommend that you should look for a book and a pen. I always advise students for that, because you cannot just be watching the video without you jotting relevant points. Okay, so without wasting much of your time, let's get started. Okay, so that is the question. Okay, so the question reads: the table below shows corresponding values of x and y which approximately satisfy a relation of the form y equals to a power n power x. Okay, where a and n are constants. So this is the table here. Okay, our x values are 2, 3, 4, 5, 6, and our y values are 13.6, 27.2, 54.4, 108.8, and 217.6. Okay, by drawing a suitable linear graph, determine the values of a and n correct to one decimal place. So this point here is very important. Correct to one decimal place. Okay, because the question asks that you correct to one decimal place. If you go and put two decimal places, you lost that mark. You lost that answer mark. Okay, so let's continue. So the Roman 2 of the question reads: given that x equals to 0.2 is a first approximation of the equation f of x equal to 0, where f of x is x cubed plus 3x squared plus 1. Use the one iteration of the Newton-Raphine procedure to obtain a second approximation to the root of the equation, giving your answer to two decimal places. Okay, all right, so that is the question. So we will be tackling the solution step by step. So please stay tuned for the solution. Be attentive to get some relevant points about this video. Okay, all right, so let's look at the solution. Okay, so y equals to a n power x. So this is the question that was given to us. Okay, so yeah, this is an index equation, so we can actually tail log of both sides of the equation. Okay, for us to look for us to, let me just say, we should linearize the equation. Okay, so those of you doing physics under data analysis, yeah, those of you doing physics under data analysis, right? In fact, these equations of this form are mostly common under data analysis. Okay, for in A-level physics. Okay, so when you encounter a equation of this form, right, just take log on both sides of the equation. Okay, so taking log of both sides, we have log y being equal to log of a n power x. So by applying the laws of logarithm, okay, by applying the laws of logarithm, we notice that when a term is multiplied by another term, we actually use the addition sign. Okay, so log y equals to log of x a n power x implies that log y will be equal to log a. Since this is a multiplication, I will use the addition law. Okay, so it will be equal to log a plus log n power x. Okay, so this is it here according to the multiplication law of logarithms. Okay, so we have now log y equals to log a plus log n power x. Okay, now here I will apply a law of logarithms that if the log of something is raised to a power, you bring down the power, okay, so that the power will multiply to the log, okay. So at the end of the day, we have log y be equal to x log n plus log a, okay. So I've just reversed these two. I've bring this log n power x here, and I've taken this log of a to the other side, okay. So that is it. So now it means from here, right, we are actually plotting a graph of log y, and we're plotting a graph of log y and x with slope log n and intercept log a, okay. So this is a straight line graph, okay. It's a straight line graph actually. So normally this is helpful for physics students. All linearized equations, okay, all linearized equations are actually straight line graphs, okay. So that is it. So that is an important point that you just need to jot down, okay. All linearized equations are straight line graph, okay. So that is it. All right, so now we are plotting the graph of log y against x with slope log n and intercept log a, okay. It means we have a positive intercept, okay. So that is it. All right, now so this is our table of values, okay. So this was the given the given values, x values and the y values, but now we are plotting a graph of log y. So it means we have to obtain log y, okay, log y against x, okay. So it means I'm to obtain log y. So this is my log y here. How did I obtain this log y here? It means I'll come to this value of y, then I take log of this value. I take log of this value, okay. So so you can take a calculator. So let me just take my calculator, and then I punch. If I punch log, let me say log, I punch log 13.6. My answer is 1.33. Let me say 1.335. But I just included 2 decimal places. 2 decimal places is just 1.3. Okay. They do the same here. You take log of 27.2, it will give you 1.43, and similarly the same here, and the same goes here and here, okay. So that is it. We are plotting a graph of log y against x with intercept log a and gradient log n, okay. So that is it. So this topic is actually very important. It always comes this topic, this graph stuff, okay. It always comes, so it is very important. All right, so let's continue. Now this is a graph. I've already plotted a graph, okay. So this is a graph, right? So plotting my straight line. So if I draw my straight line, okay, that is my straight line linking the points, okay. So from when I was plotting the graph, right, I calculated the slope already. So my slope gave me 0.217, okay, and my intercept gave me 0.954. My intercept means where this line of best fit cuts the vertical axis, okay. So that is the intercept, okay. So that is it. Now notice the values range from 1. So for the vertical axis, for the log y axis, right, so we have what it starts from 1.3 right up to 2.34, okay. So that is it. And for the horizontal axis, that is the x-axis, we have this. So this is it. And the values here, we have 6. So that is it, directly plotted to 6, okay. So I plotted the graph already. So that is a graph, okay. Now from this graph, right, we are going to use this value here, these values, to look for our a and our n, okay, to look for our values of a and n, okay. It means we have to obtain this value, this n value here. We have to obtain n and a, okay. But we already know that wait, there is a mistake here. Here was supposed to be log y, not y. Sorry, it was supposed to be log y. Let me just correct it. Actually here was supposed to be log y. So we have log. Yeah, it was supposed to be log y, so that is it. All right, so as I said, we are going to use these values. This my slope here, and this my intercept. Okay, so for those of you doing physics, right, this point here is very important because they will give you a graph that you should plot the graph, and then you should calculate the intercept. Okay, so when the graph begins from 0, right, you can actually reach the intercept directly from the where the line of best fit cuts the vertical axis. Okay, I can conveniently read the intercept from here because this graph begins from 0. Okay, but in cases like in physics where the graph doesn't actually begin from 0, so it means you have to use this format. Okay, it means you draw a triangle to calculate a slope, right, you choose 2 points used in calculating the slope for you to calculate the intercept. Okay, anyways, where I'll be uploading data analysis videos, I'll explain that better. All right, so let's move to the next slide so that we can actually work on this. Okay, all right, so as I earlier said, from this our equation here, we are to obtain n and a. Okay, so from the calculated values of the slope from the graph, that is this value here. Okay, the slope is actually the slope was actually log n. Okay, but log n, yeah, this is our slope here, and this is our intercept. So the slope is actually log n, but log n is 0. So since log n is a slope, it implies that the slope log n will be equal to 0.217. So also for the intercept, we know that our intercept was log a. This is it here. Our intercept is log a. Okay, so it means we have to equate this intercept, which is equal to this value here, which is 0.958. Okay, so it means our log a is just equal to 0.958. This is not the value of our a. This is the value of log a. So the value of log a is 0.958, and the same goes here. The value of log n is 0.217. Okay, so that is it. Okay, now we are going to handle each case separately. We'll handle this case and this case. All right, so if we begin with case 1, so if I begin with case 1 here, that log n equals to 0.217. So it means this is my log n. Right now, there is something important here that I would like to explain. Okay, and you can equally jot it down because it is very important. Okay, so you notice that many students will be confusing where this 10 is coming from actually. Yeah, so what is happening here is that we have log n being equal to 0.217. Okay, so 0.217, so it means our n is just equal to 10 power 0.217. Okay, why? Because if the base of the logarithm is not given, we consider it to be of base 10, or to be in base 10, sorry. Okay, to be in base 10. So in mathematics in general, if the logarithm is given without a base, it means that logarithm is in base 10. That is why for me to come, this is the logarithmic form, so this is the index form. For me to convert now from the logarithmic form to the index form, it means I have to send that base this other side. Okay, such that the base will be raised to this power. That is why I have n being equal to 10 raised to the power 0.217. Okay, I can actually convert from the index form back to the log form. Okay, so if I'm to convert from the index form back to the log form, it means that I'm just going to send this base again back to this other side. Okay, and then I include my log there. Okay, so if the base 10 is going back, it means since since this lock is actually in base 10, it means if the base 10 is going back, we actually implement this lock. Okay, so that is it. All right, so if I take my calculator, then I punch, let me just do it. Let me take 10 power, just take 10 raised to the power 0.217. So my answer is 1.648. But the question said we should leave our answer to one decimal place. So to one decimal place, we have 1.6. Because this point here, as I earlier told you in the question, this point is very, very important. If the question says to one decimal place and then you put 2, you lost this answer mark here. Okay, yeah, so that is it. All right, let's continue to let's go to case 2. So our case 2 means we're actually dealing with this log A being equal to 0.958. So it's the same procedure. It means I will actually convert from the log form to the index form. Okay, so that is it. So implies my A will be 10 raised to the power 0.958. Okay, so therefore my n equals to 1.6 and my A equal to 9.1. so that is my values. Those are my values of n and A. All right, so let's continue. Okay, so the Roman 2 of the equation reads, given that x equals to 2, x equals to 0.2 is a first approximation of f of x equal to 0, where f of x equals to x cubed plus 3x squared minus 1. Use the iteration of the Newton-Raphins procedure to obtain a second approximation to the root of the equation, giving your answer to 2 decimal places. This point again, 2 decimal places. It is very important because if you decide and put your answer in 3 decimal places, you will actually lose that answer mark. Okay, so to 2 decimal places, it is very important. All right, so let's dive into the solution to this other part here. All right, so what is Newton-Raphins theorem all about, or Newton-Raphins procedure all about? So Newton-Raphins iteration formula states that if you are to obtain a next term, right, a next number, say 5, it means you have to increase that number. It means you have to increase the previous number by a factor of 1, such that f of 5 divided by f prime of 5 will give you, no, sorry, let me just put it this way. If Newton-Raphins iteration formula states that if you are to obtain a next number, okay, use the previous number minus f of that number divided by the derivative of that first number. Okay, so it means that x into xn plus 1 equal to xn minus f of xn divided by f prime of xn. Okay, so that is it. All right, so this is our f of x. Okay, so it means from this formula, right, from this Newton-Raphins theorem, or this formula, or the iteration formula, right, what we need f of xn, where our xn here is the first value. Okay, our xn is the first value, which is 0.2. This is our x1, actually it is 0.2. okay, and then we need our f prime of xn. It means we need our f prime of this first value. Okay, so this is our f of x. So firstly we know that from the formula x2, so it means, let me use one iteration of the Newton-Raphins procedure to obtain a second. It means we are obtaining x2, a second approximation to the root of the equation. It means we are actually obtaining x2. Okay, so our x2 will just be equal to x1 minus f of x1 divided by f prime of x1. Okay, so now I'm doing my f of x1. Okay, this is my f of x1. Okay, so my f of x1, but I know that my x1 is 0.2, so it means I will substitute my f of 0.2 in f of x. Okay, so that I'll have f of 0.2 being equal to 0.2 cube plus 3 times 0.2 minus 1. Okay, so at the end of the day, I'll have my f of 0.2 being equal to negative 0.392. Okay, I hope it is clear. So this is, I explained it again. This is, let me explain again. This is my Newton's-Raphins iteration formula. Okay, so this formula, what I need f of xn, where xn is my first value that is given, and that my first value that is given is actually 0.2. Okay, and then I need the derivative of that my first value again. Okay, so now my f of my first value is my f of x1, and the x1 given there is 0.2. Okay, so I will solve for f of x1, which means f of 0.2. so it means where I will find x, I will put my 0.2 there, since x1 is equal to 0.2. Okay, so that is it. Therefore we have f of 0.2 being equal to 0.2 cube plus 3 times 0.2 minus 1. And if you input this in the calculator, you have f of 0.2 as negative 0.392. Okay, so that is it. All right, so what next? So now we are actually we are looking for the first derivative of this equation here, f of x. Okay, it means the first derivative means we are actually differentiating. Okay, so it means we are differentiating this function, this f of x with respect to x. Okay, so if I differentiate x cubed, I will have 3x squared, and oh sorry, here was supposed to be squared. There was supposed to be a squared here, so you can put it here. There was supposed to be a squared there. So if I differentiate if I differentiate 3x squared, I will have 6x. Okay, now this is a constant. One is actually a constant. If I differentiate, in fact, in general, if you differentiate a constant, you will have 0. But why in integration, if you integrate a constant, you will not have a 0. Okay, so when differentiating a constant, since when dealing with differentiation, right, you are dropping the power by 1, while with integration you are increasing the power by 1, and therefore differentiation is a reverse process of integration. Okay, when you are increasing the power by 1, it means you are integrating. If you are reducing the power by 1, it means you are differentiating. Okay, so if I differentiate x squared, it means I will take this 2, I bring it down, multiply it with this 3, and then I drop down the power by 1, such that I'll have 2 times 3, which is 6, then 6x, then 2 minus 1, which is 1. That's why we have x here. Okay, so f prime of x is just equal to 3x squared plus 6x. Okay, so that is it. Now that we have obtained our f prime of x, it means we can actually solve for f prime of x1. Okay, and f prime of x1, and we know that this is our x1. Okay, so our f prime of x1 will just be f prime of 0.2, which is equal to 3. So it means I'm substituting this f prime of x1 in this my f prime, this my new equation here. Okay, so I'll have f prime of 0.2 being equal to 3 times 0.2 squared plus 6 times 0.2. So at the end of the day, my my f prime of 0.2 is just going to give me 1.32. so that is it. So it means I've obtained my f of xn, which is my f of x1, and I've obtained my f prime of, or the derivative of my x of 1. Okay, my x1. Okay, so let's continue now. So now from here, since I know this value, I know this one and I know this one, I can just substitute them. Okay, so my x1 value is 0.2 given in the equation. This is it here, 0.2. And then what do you notice about my f of x1? My f of x1, which is my f of 1, is negative 0.392. That is why I have minus. So this minus here comes from this part here. Okay, so I have x2 being equal to 0.2 minus 0.392, then divided by 1.32. Since my 1.32 is my derivative of my x1. Okay, so that is it. All right, so implies that my x2 now will just be, now negative will give me positive. Okay, so we have 0.2 plus 0.392 divided by 1.32. okay, so my x2 is equal to, so if I take 0.392 divided by 1.32, I'll have 0.297. okay, and then I add it to this 0.2. okay, so it therefore means that my x2 is just equal to 0.497, which is approximately 0.50. okay, why did I approximate it? Because the question said give your answer to 2 decimal places. So this is my answer in 2 decimal places. Okay, so this brings us to the end of the video. Okay guys, stay tuned for more past questions. So this is actually June GCE June 2017 question 4 paper 2. okay, so this is a step-by-step detailed explanation of the question. Okay guys, stay tuned, and I recommend that if you find the video helpful, please like, subscribe, and share to your friends. Okay, see you guys in the next video.